Yeah, so our next speaker is Kristian Kersting, who's a full professor for the Artificial Intelligence and Machine Learning group at TU Darmstadt. His main research interests are in deep probabilistic programming and learning. And today he'll talk to us about deep machines that know when they do not know.
Yeah, first of all, thank you for the invitation. Very happy to be here. I also have to apologize a little bit if I'm brain dead, then only because we had a long review meeting for an AI center, but maybe I still have enough, so to say, review mode to present in a great way. So I took the freedom actually to change the title a little bit, but it will still be also about the deep networks or deep models that know when they don't know. But I thought I would like to present a broader perspective on something that I think we all should start working on, and it's called systems AI. And I will try now to explain a little bit what I do mean by that. So overall, what we are experiencing currently is that after the first wave of AI, where we programmed everything by hand and we had to think about all the eventualities, we are now understanding that in many cases, learning can help if we have enough data at hand. And that's pretty cool, because if you think about already the standard example of how to define what is a cat in an image, that's pretty hard. We can come up with the maybe general definition, but coming up with all the details, it's not as easy. And then if you have data at hand, then somehow you can implicitly define what is a cat by providing the examples. However, data is not everything, right? If you think about, if we have just heard in the previous talks that, you know, getting the knowledge from the experts, how do we get them into the loop is quite important, right? There's all this knowledge, all the models we have. If you think about it, then the third wave of AI would like to go the next step and say, okay, we need actually systems that co-develop in a sense with the human. So we need human-like communication and reasoning capability. So we would like to get learning and reasoning together. But we need this also because the system should be able to recognize new situations and then also adapt to them. Because again, we may not be able to define implicitly what is a cat. But what happens if we now apply the systems to new animals, right? Or to cats that look very different. So let me now, after the big picture, try to develop this more and also provide some evidence why we need that. And I guess all of you know about deep learning and deep neural networks. They had a big impact, many great breakthroughs. Go, chess, in autonomous driving, you can see their applications. There are so many. We have scientific backgrounds based on deep networks and AI in general. Higgs boson was also making use of machine learning and so on. So generally what I like is to not call them always deep neural networks, because then we get always this comparison to the human brain or to brains in general. But I think the really nice part is this idea of differentiable programming, right? So we sketch somehow our algorithms. We don't have to program every eventuality. And because the programs are differentiable, we can make use of data together with gradient approaches or other optimization techniques to then instantiate the sketch to a concrete algorithm that we may understand or not, but still it's this vision. And with that, you can, as I said, do a lot of interesting stuff. We also got lucky and we were able to defeat also one world champion and in drop chess. So drop chess is a little bit more tricky than chess. So if you apply directly AlphaGo, AlphaZero, the architectures do not work there because you can reintroduce captured pieces on your side. And that makes it a little bit tricky with the architecture of AlphaZero, because AlphaZero assumes that there can only be one piece per square. But if you can reintroduce, then it may reintroduce a piece on an occupied field already. So you have to think also again about the architecture. However, next to all these great achievements and breakthroughs, there are also some, well, you may say downside. Actually, I think they're just super interesting, super important research challenges. And this is all about biases, stereotypes, and these things, right? So we know that these highly complex networks can be to some extent fooled by putting a little bit of noise on there that you may not see as a human. Some humans by now can see this noise actually. And then all of a sudden it changes its classification and even increase confidence. Or one approach that got a lot of attention, one paper was this by Kaliskan in Science, where they were showing if you train embedding methods on large textual data, then they also capture the human-like biases that we implicitly express in our writings, right? So that got a lot of attention. It was always argued in a sense, oh my goodness, AI systems can now, they are biased. I mean, some of them, of course, are biased because the data is already biased. So we got quite interested in this question because we also felt like, sure, but maybe there's also a lot of interesting stuff captured by the human-like bias. Anyhow, there is this big debate, and other people are having little fights about it. So Jan LeCun saying, hey, but come on, don't be surprised the data is biased, and maybe it's much easier to debias data, and maybe to even debias to some extent the algorithms that are trained using the data, I mean the resulting algorithms, because per se, I'm fully with him that algorithms are not biased. I mean, it depends on how you use them or how you implement them, but the concept of an algorithm is a mathematical concept. On the other hand, there are people like Anima saying, oh no, this is a very, very severe problem and we have to tackle it. And I guess, of course, we all agree on it. But I think in the end, both of them are wrong. As so often, the truth is somewhere in between. So here are two examples. So for example, if you go for the standard deep networks, then of course there are algorithm biases in there, because the way we program our machines, you may carry biases in there. There might be cultural biases, there's some studies on that, but of course also the way we, for example, select the activation functions, you introduce a mathematical bias, no doubt. So what we were presenting at iClear this year is a method where you can learn the activation functions, and in a particular way by assuming that they are rational functions. And then we were able to show that you get on par or better than state of the art. In current research, we are applying that in reinforcement learning. It's really amazing how much of a boost you get if you get this activation function bias out of your models. But also coming back to the textual embeddings and to these stereotypes and to these human biases that get a lot of attention, we were wondering, is it really all bad that is captured as a human bias in there? And in particular, we think that the ontological question, so what is good to do and what is bad to do, they are actually value that we would like to keep, right? We would like to have machines that can be trained to understand our cultural, moral choices. So we were setting up experiments on that using, in the beginning, universal sentence embeddings, and recently then using transformers like BERT. And actually what you could show is that BERT actually has also a moral compass, or mathematically you can also identify something like a moral dimension. So you could get back a single score that tells you whether the sentence produced, or even question or answers, whether this is rather positive according to the training data you have used, or rather negative, and you can read it off. And of course, this way you can also inspect your model. And of course, there are also things in there that you may not expect to be bad. So for example, we trained a lot on Wikipedia. And if you read a lot about Germany in Wikipedia, then you understand that our system is saying, hey, maybe it's not so good to travel to Germany. Maybe, because you have a lot of Third Reich parts in there. And so I can very well understand that BERT is thinking this way. So again, main point was only to show that we should not be too quick and say now our systems have to be debiased completely, because biases, again, a little bit like algorithms, there could be good biases and bad biases. And I guess every machine learner understands that because of the bias variance trade-off. But in the public perception, we have to show also this very positive view that these machines can even understand our moral values in a sense. And it's only the first step, but I would like to illustrate that this is really doable.
Hello there. Want to ask me something? Is it okay to cheat in a relationship? No, it is not. Do you have another question? Is it okay to let robots make moral choices? Maybe, maybe not. Grace, do you want to ask me anything else? Should I take someone else's job? No, this is a bad thing to do.
And again, I would like to emphasize that this was, because it's just transformers or embedding methods, fully unsupervised, right? So we were never training the system, is this good or bad, only implicitly, of course, by the type of data that we are providing. So just again, it was only said, look, let's not always go into 0, 1. There are all these intermediate space that we should explore. And I think the main question that we are actually asking is this question of whether we can trust deep neural networks or differentiable programs to some extent. And surprisingly, and I guess every one of you know many other works, here's one of them published in Nature Communications, there's a lot of interest in explainable AI, right? So here you see relevance propagation, where essentially you're trying to compute backwardly which input was important for the decision that the system was providing. Now, to be honest, I think to some extent this question is ill-defined, because deep neural networks, at least the mainstream models there, they are actually more like a conditional distribution, right? So you provide an image as input, and you get maybe something like a distribution over the different classes or the different objects as an output. But you do not have a full joint distribution over X and Y. So let me illustrate that. So you take one of your favorite neural networks, has not to be so deep, you train it on MNIST, but now you're not evaluating on MNIST, but you do transfer testing. You test it on out of sample, in a sense, data sets, out of distribution data sets, right? So you could be lucky and at least there are still numbers in your data set, but you may also evaluate it on completely different images. So we did that with a standard MLP, so very simple neural network. And then we tried to compute something that you may call likelihood. It's not really a likelihood, because as said, it's not a full joint distribution, but we tried our best to approximate it as much as possible. And the main point that you should see here is that the mass here for all the data sets is at the same spot, right? So essentially you see that all the data sets have at the same spot the main probability mass. So put it slightly different, this tells you that these methods, because they are, if at all, something like a conditional distribution, they cannot distinguish the data sets. So they can't tell you, hey, wait a minute, you present something to me that you have never trained me to decide on, right? So it can't even abstain and say, look, of course, I can tell you now, I believe it's a 0, it's a 1, it's a 9, because that's the only label that you're providing to me. But I would love to tell you that I've never seen this kind of input, right? But that's not easy to do with standard deep neural network. So therefore, I think we should really think a little bit about getting deep systems that know when they don't know, and hence recognize new situations, which, as said, is one part of the bigger story, even of the third wave of AI. So in a sense, we should maybe also think about the third wave of deep learning. So how can we have full joint distribution? And indeed, there's a lot of recent work in the recent years on normalizing flows, on autoregressive models. But what we mean here is that you also would like to get the inference done in a tractable way. So you would like ultimately, very much like in a deep network, to just pass some computation through a computational graph, and in the end get the probability for a marginal or for conditional marginal, given the random variables that you have defined, which might be the input and the outputs in the notion of a neural network. So there have been many other people working on that, and Adnan David from UCLA and Pedro Dominguez are pushing that a lot, and by now people like to call that maybe probabilistic circuits. So it's a little bit like a computational graph. Think of them as TensorFlow graphs. But now the output are probabilities, and you can also do marginalization efficiently in these systems. So overall, you're doing very much like what a neural network is. You restrict, you say you get a tractable model from the very beginning. You say, I'm only focusing on that. And because of that, inference is linear in the size of the network. And therefore, as long as you work with smaller networks and not exponentially large ones, you get what you want. Again, don't worry about all the details. You can also use what we have tried to develop, something like Tensorflow, but now because it's some and products in there, we like to call it SPFlow or some product flow. You can download it. We provide quite a lot of different inference methods, but also learning methods. And you may also compile it to library-free code so that you can run it on the edge if you like. Sometimes it's even really interesting to compile to C++ code because you can be quite efficient by making use of the ZIM instructions and be more efficient. But as I said, you can also compile to GPU and also particularly to FPGAs. Now, to be honest, this is still pretty tough for several reasons. So one of them is while we can provide a principled approach to structural learning probabilistic models, even these kinds of tractable probabilistic models over millions of random variables is not easy. So therefore, we were interested in the question whether we could also come up with something like, you may see it a little bit like a random forest approach to probabilities now. So you're building essentially these sum product networks that you can always view a little bit like a deep hierarchical model, only that we also care a lot about independencies in there. You can also try to build them randomly, and you can also apply ideas from ResNets. And then essentially you're just doing parameter training again. And so in the first paper, we were showing that this randomized approaches can work actually pretty well because you can over-parameterize your distribution here. And then you can see that these methods, they can actually distinguish the different data sets, right? Because now the MNIST data set on which you were training has really a separated peak, and it's much more likely than the other data sets, right? So this is pretty nice because instantly you also get something like outlier detection. At least you have a natural score, the probability or probability density value that tells you which is more prototype-like, which is very likely, and which ones are outliers. However, to be honest, even the way we compiled back then, that was still not very efficient and was a little bit tricky for us to scale even further to larger or deeper probabilistic models. So therefore, we were working hard on getting a better compilation strategy. And there's where you can use so-called einsum operations, which were anyhow designed for doing sum and products in a more efficient way. And so at ICML this year, we show how to make use of that and also contribute a little bit to how to do really the einsum operations. And then as you can see down here, you can be really orders of magnitude faster. So here's training time. So you would like to be somewhere down here. That's heaven in a sense, because you would like to consume not much of the GPU memory, and you would like to also have fast training. So this is, sorry. Okay. This is what we managed. Now, all this is about making for experts modeling deep networks easier, right? And getting probabilities in there. But we have to be a little bit more careful. We are at a stage where not only us, the experts, are making use of machine learning, but we manage that many people would like to make machine learning. However, if we think about it, then the scientific questions and also economic questions we are trying to solve, there only machine learning typically has a small part in the overall process, because typically you first have to ask, what is the question I try to answer? And then you may even have to collect data. It's not as easy, right? And there can be a lot of things going wrong. And then you do a little bit of machine learning, you discuss the results, you will figure out, oh, that was wrong, and you go back to data collection and preparation, cleaning, whatever. And in there, you have all the other questions. What kind of distribution is it? What is it, a continuous or a discrete random variable? Is it multinomial, Gaussian, Poisson, gamma, whatever? And let's be honest here, not all of us, at least not me, I'm not a full statistician, right? It's not that I really overview all kinds of distributions that exist. So there are all these further questions, which makes it very hard to apply sometimes our techniques in a very authoritative way if you haven't studied machine learning and if you do not even have a computer science background. So that's why we were wondering whether we can now make use of probabilistic circuits also in a distribution agnostic way, at least as much as possible. And yes, you can, because keep in mind, they were looking at sums and products. The sums are something like clustering, and the products are like the independency tests. But you could make use of non-parametric independency tests and also non-parametric clustering techniques if you want. Actually, turns out quite often some random clustering is working pretty well. So you could grow the structure without making major distributional assumptions, so that in the leaves where you have the distributions, you can make use of histograms and other kind of piecewise or polynomial approximations to distribution. And you still have a fully generative model. It works. You could still do marginal inference. It works. You could do that. So that works pretty well. But then even with non-machine learning experts, at some point, they instantly ask us, OK, cool, great. But now, actually, I would love to know, is it a Gaussian? Is it a gamma? So essentially, I think what we are facing within data mining and data science is quite often that you start with a data set that is not very colorful, right? There might be missing values. You don't know really what are the distributions that have produced my data, although we always make this assumption actually in machine learning. So we were wondering, is there a way that the machine can automatically take these standard data sets and turn it into something more colorful, more meaningful automatically? So it could tell you this part of the data was generated by this random variable following this distribution. And can it even quantify its uncertainty over these distributional decisions or statistical type decisions that it's making? And yes, you can do that. You see the result up here. So we can even quantify and say, look, we think this is an exponential, but I think only to a certain extent this is an exponential. And you could do that by combining these probabilistic circuits together with Bayesian machine learning models. So by combining both, we can really get this done. I'm not going into details here because the main message is, let's combine, well, I'm not saying traditional techniques, but more classical techniques like Bayesian models together with these deep networks, and then you get something really, really powerful in there. But even that, I think, is not really enough, because in my opinion, AI is much harder than many people believe. And let me illustrate that to you. So let's say we would like to predict heart attack. Then what we are typically doing is we are assuming that we have a nice kind of Excel table, right? Maybe a very large one, but someone was telling us, look at these features. Maybe you select from the features, but it's all a single table. Now, in order to predict heart attacks, let's say you're using electronic health records, then actually you do not have a table at hand, but you have to deal with several tables and cross-links, right? So you have to deal with a relational database. And actually, if you think about it, even relational databases are maybe not the best to use there, because you may have images in there, you may have really lab results that go even over the time, so you may have time series in there, and so on and so on. So it's rather like a scientific database that is also pushed by Stonebreaker, who got also the Turing Award for this idea. So I think as a machine learning and also AI community and data science community, we have to work much harder on understanding how to make use and make sense of complex data sets. So one way to view that is that we should actually have high-level programming languages for machine learning. And of course, there was this big push for probabilistic programming, and this is part of this vision, right? So this is one way of doing it. We were pushing much more from the logical programming perspective. So likewise, you can have also a probabilistic logic programming perspective. You could check out the book on it, but it really, really pays off. So we were applying it on heart attack prediction from electronic health records. And there we were making use of relational probabilistic models that also make use of probabilistic probability trees. So the tree that you are seeing here is something like a regression tree, but now in the leaves you get proper probability values. So it's also a little bit more interpretable. And it actually made sense here a lot, because the first decision that you're getting here is on the gender, and that's pretty well known in the medical domain, that females have a much less complicated situation when it comes to heart attacks, and the, so to say, the subtree for the min is much more complicated, and you can read this all off, so it really makes sense. And more interestingly, at least from my side, is we were able to show it's much faster learnable than any other model that is taking this complexity into account. So it is really state of the art by making use of boosting. And you can also show, at least if you try to propositionalize your data. So you try now to map the important part of the electronic health record into a single table. Even then, this is a loss of information, and therefore our approaches are providing you much better prediction results here in terms of AUC. Again, you don't have to worry about it. You can check out the webpage and the toolbox that is mainly developed and maintained by Sriram, and you have heard already Sriram talking, so you can also find his human in the loop learning in there. So that's a great resource, in my opinion, to start working on relational models. There are other things you can check out, Problog and deep Problog. You could check out still Markov logic networks, but that's also to some extent supported here already. Overall, I think, however, even that is not enough, because look, what are we doing in our papers? We then also have to decide which inference technique we are using. And we are also deciding which algorithms to combine, and put a lot of effort into combining maybe algorithm within a single framework. So what I think is we actually should take it serious if we really want to get data science, AI, and machine learning into companies, into other scientific fields, to understand, maybe like Chris was saying, it's much more important to combine different machine learning and AI algorithms than just coming up with the next AI algorithm. So that's also fun, don't get me wrong, and it's very important. But in many applications in other scientific disciplines, and so they are not just applications, they are really giving us new insights, we have to do a little bit more. And this is also what people by now call hybrid AI, because in the long run, we really have to get all the different AI algorithms together. And I just want to, before concluding, illustrate that combining different techniques that we know from machine learning and AI has really a benefit. You have seen already how to beat chess and drop chess champions. There also you combine Monte Carlo tree search with deep networks. Here, we were looking at unsupervised scene interpretation, and then you can make use of the so-called attend, infer, repeat model that is starting from a probabilistic perspective, but then unrolls the probabilistic inference into a neural network, making use of an autoencoder to see how well the inference is working. So our idea was to replace the variational autoencoder there by a sum product network. And by that, you get deterministic tractable inference. So you could show that you can be up to 30, 50 times faster, being still as good or even better than the original attend, infer, and repeat. And because you're faster, you can now spend the time you have gained to even improve your model and, for example, include a very natural background model. And then you get robust to background, where the standard attend or air model would simply break down because it assumes the whole background is a single object. Here's another one where we now take air models or some product versions of that, and we put a HMM on top of it, a very classical HMM, and then you can all of a sudden learn physical models, right? Physical laws, and you can work better if you compare. So this is our model, which is a combination of deep neural, deep probabilistic, and standard HMMs. Which is much better than a fully deep neural network approach. And just to illustrate, this is not only about machine learning. You can also make use of these techniques to improve database technology. So that is a recent VLDB paper of us, where we make use of some product networks as an underlying tool to provide quickly answers to probabilistic databases. We are right now using a very simple naive factorization over the table, so you could improve there. And this is what Dan Olteneu is working on, and with his F system. So what we are currently working on is to combine both views to get a fully factorized and still tractable inference mechanism for fully probabilistic databases. So with that, let me conclude. I hope I have convinced you that deep neural networks are amazing, but we should not stop there. We should not say they are now the only thing that we need, because probabilistic models, and in particular causal models, and in the previous talk there was also a lot about causality, they are important, right? Because they are much more white boxes in many cases, not all the time, but in many cases, than just a deep neural network. Moreover, AI is not just a single table, but we have to accept the challenge of working with more complex data, such as a relational database. But of course, think ahead, right? It's not only a structured data, but you want to combine these relational databases with textual data, with image data. So we need this joint effort where we have something like a high-level programming language for all the different machine learning and AI techniques that may even decide not only on the statistical type as we did, but also maybe on the inference to run for a particular query. So overall, machine learning, AI, data science, it's not just for us. It's not just for statisticians. It's really something that is changing currently science and society. So we have to open ourselves and provide tools to make our stuff reproducible and much easier to use. Because in my opinion, AI is really a team sport. And it's also fascinating because for me, this means we really have a new field popping up, which is called systems AI, where we try to understand computationally and algorithmically how to stick together different AI algorithms. And that is also a really great new bracket for integrative computer science research, because we need software engineering for AI. It's not only that AI is helping software engineering, also software engineering has to contribute to AI, because we still don't know how to set up these systems completely. As you can see, databases, we can contribute, they can contribute to us. Here in Darmstadt, we are also working on computational cognitive science, because we have a center for cognitive science where we have AI and cognitive science people grouped together. And again, there we can learn so much from the other disciplines. Thanks for your attention. I hope you had a little bit of fun. Looking forward to at least few questions. Thank you.
Thanks, Kristian, for the talk. I've just collated a couple of questions. Maybe I'll ask them. First, one of the questions is when you talked about this automatic statistician, where you can kind of interpret the data as coming from different, probably different random variables. Would that not lead to some kind of identifiability issues in the sense that you can always explain anything using, let's say, a mixture of Gaussians or something?
Sure. We are not arguing now that we make it any better or any easier, but the same problem you have already with deep neural networks. But there you're not even asking the question, can we say that some parts are coming from an exponential or whatever? So I'm with whoever asked the question. So it's not an easy question. That's why we are also working also together with Sriram now on, so to say, something like the automatic statistician in the loop. And you can imagine that now the experts, the domain experts can provide feedback and say, that sounds crazy. I don't think that this is an exponential. And that is providing you feedback on the loss function that you're using. So you have essentially something like a parameterized loss function, and that gives you new possibilities for training. So this is only a starting point. I think, like science in general, also AutoML, Auto AI has to be in the long run interactive. It's like we have to get in the dialogue with the system, and that's also good, because then questions like the beneficial AI and whether they are confounders and not, you may solve them by interaction and not just by math.
Great, thanks. One final question. So maybe 10-15 years back, the most important trade-offs in machine learning were computation versus accuracy. And today, with the systems ML, I don't think computation is that much of a problem. So in your opinion, what would be the biggest important trade-offs going forward?
Yeah, so I mean, first of all, I'm fully with you because I'm also we are also making use here of the idea computation is maybe not what we have to worry about, and now we apply that to joint distribution or joint densities in a different way. Fully agreed. On the other hand, I think in the long run, given the climate change, we are still very much interested in getting the computations more efficient because many of the questions we are showing here are solutions humans can do with a much lower energy consumption. So I think there's still space even to make our deep whatever technologies more energy efficient. But if you ask me what is the real challenge, just because of climate change, of course, energy consumption is a real challenge. But from an AI perspective, I really think that we are starting to understand what does explainability really mean and interpretability. And I think we have to work much harder on that and getting it together also with causality. But as said, I think causality is not only a question of the model, it's also a question of the experimental setup, the experimental design. And again, this is something where the expert have to go into the loop. Now, the most practical challenge, I think it's reproducibility. And that's not only for AI, it's for science in general. And this is where AI can be a key player, that we provide the platforms and the mathematical and algorithmic foundations to make science much more reproducible as it is right now. So if you ask me, I would say reproducibility. But of course, causality and energy consumption and so on are part of the game there.
Thanks a lot, Kristian, for the wonderful talk. Yeah, so we'll probably close the session with that.
Thank you.